Hello everyone. So in today's video we're going to continue where we left off previously. So in the last video we discussed the effect of or we left off with discussing the effect of altitude and outside air temperature on the angle of climb, especially for the jet. So we're going to have a look at the effect on the propeller driven aircraft. So the effect of altitude on the propeller driven aircraft. Okay, so here we have the formula. Is the sine of gamma is thrust minus drag over weight, and the question is, again, like if you increase the pressure altitude, which means that the pressure is decreasing and the density is decreasing, what happens to the angle of climb, to the gamma, right? This is the question. Okay, so let's look at the denominator again. Like, what happens to the weight if you increase the pressure altitude? The answer is that nothing happens to it. So then there's the second question, like what happens to the excess thrust when you increase the pressure altitude? Okay, so again we need to plot the thrust and the drag curve of the propeller-driven aircraft to get an answer for that in the function of the calibrated airspeed. So here we're going to have the thrusts of the propeller-driven aircraft and the drag. Okay, so the drag looks something like this. So there you have the drag curve of the propeller-driven aircraft. Looks exactly the same as the drag curve for the propeller-driven one, or sorry, the jet. And there you have the thrust curve for the propeller-driven one. Okay, so thrust, and let's say this is for HO, so the low pressure altitude one. And if you remember, we said that the greatest excess thrust would be realized well below the VMD, so somewhere around here. So this would be the Vx for the propeller, actually Vx HO prop. So basically propeller driven speed for best angle of climb at low altitude. Okay, so what happens with the thrust curve? Even more so, what happens with the drag curve with regards to the calibrated airspeed if you go ahead and increase the pressure altitude? Well, the answer is simply speaking that to the drag curve nothing significant happens with regards to calibrated airspeed. And the answer with the thrust curve is that the thrust is of course going to be reduced. The thrust is going to be reduced in such a way. Okay, and what is visible, interestingly speaking, is that the excess thrust is going to be of course visibly lower, but the point for the highest, or the speed for the best excess thrust, is going to occur at a higher speed. So this right here would be the Vx H1 prop, right? So what we can see is that altogether the excess thrust has reduced, right? So we went from this much to this much. Of course there's some difference down here as well, but of course you can still altogether that the yellow vector is smaller than the orange one, so therefore the excess thrust in case of the higher altitude is lower than the lower altitude, and it occurs at a higher speed. So the Vx increases as altitude increases. So and of course the excess thrust decreased. So there's the answer to the initial question, which we asked right here, like what is the effect of the pressure altitude on the excess thrust and therefore on the angle of climb. Is gonna with increasing pressure altitude, the excess thrust is going to reduce, and therefore the angle of climb is going to reduce as well, right? So we can say that for the propeller one, with the pressure altitude increasing, the angle of climb is going to reduce, and the Vx prop is going to increase, both with regards to the calibrated airspeed as much as with the true airspeed one. So in this case, it's true for both cases, because for the true airspeed, this would also mean like an increase. Okay. So that's the answer. As pressure altitude increases, the angle of climb reduces, and the Vx, so the speed for the best angle of climb, is going to increase, right? And what is the effect of the outside air temperature? It's basically the same effect as the pressure altitude. So when you increase the outside air temperature, you would have the same exact effect as we had in the case of the pressure altitude. So you could substitute for the THO, like the initial one, like cold thrust, and when you warm it up, oh sorry, I forgot to index this one. This would be TH1 or TH hot, right? So when we go from this curve, the one on the right to the one on the left, this could basically either be an increase in the pressure altitude or an increase in the outside air temperature, and it would give you the same exact result basically. So the pressure altitude increases is the same effect as the outside air temperature. So therefore, if the outside air temperature increases, the angle of climb decreases, and the Vx, so the speed for the best angle of climb, is going to increase, both regards to the calibrated airspeed just as much as with the true airspeed. Okay, so we're not going to go with much more of a detail than that. Okay, so let's just read off right from the Path Pilot book. So in the Path Pilot book, it says that the effect of temperature on climb performance is also significant because air density reduces as temperature increases. It's true. On hot days at the same pressure altitude, the reduction in thrust will reduce the excess thrust and hence the angle of climb. However, as many turbine-powered engines are flat-rated, the effect of temperature on climb performance is not apparent until the turbine-powered aircraft is operating in hot temperatures above the flat rating cutoff. Of course, this is for the jet, and you guys might remember the flat rating. The flat rating of a jet engine, where we had the thrust in function of the outside air temperature, and we said that until a given temperature we would have a constant thrust, and after that we would start reducing the thrust like this, right? And the reason for that is that as you actually decrease the outside air temperature, the density becomes higher, and if the engine wasn't flat rated, you could basically generate higher thrusts at these lower temperatures, which could damage the engine. So this limitation, this flat rating limitation, is there for to protect the engine basically. So it's an RPM limitation. Okay, and so this is what the Path Pilot book is referring to. Okay, so let's see the case of the engine failure. Okay, so engine failure. It's fairly apparent that we expect, of course, the angle of climb to be much reduced if you lose an engine. And initially what you would imagine is that if you have an engine failure, so basically you have a flight path angle, you have an alpha or gamma angle, and if you were to have an engine failure, you presume that this would basically like drop to half, like gamma over 2. If it's a twin engine aircraft having a single engine failure, you might presume that this is the case, but in reality, the loss of the flight path angle is actually, in most cases, much more significant than just to half of the original value. And we'll see in just a bit why. So this is actually quite huge. So it's not just losing 50% of the flight path angle, but quite a big deterioration. So let's start with the jet as to how this happens. We're not going to get exact numbers out of this whole calculation, but let's just see how this whole process is handled. Okay, so let's have calibrated airspeed, or as you might see it in the Path Pilot book as well, indicated airspeed. But we said for basically representing these kind of charts, you might see indicated airspeed in the Path Pilot book, and you might see calibrated airspeed in the aviation exam question base. For this particular kind of discussion, we can presume them to be pretty much the same, or they will basically serve the same purpose. Okay, so here we have we're going to have the thrust and the drag of the aircraft, and we have right here the thrust when both engines are operating. So we're going to say twin engine jet and single engine failure. Okay, so this is the so-called TAE. So TAE would be all engines, so thrust delivered with all engines operating. Okay, so this is a nice constant right there, and this would be the drag which is being generated at the all engines operating. And why this happens, or why we discuss it, is going to be interesting in just a second. Why we make a differentiation here. Okay, so what happens with the thrust curve when you have an engine failure? So when you have an engine failure, is a pretty simple scenario. Let me just wipe up here an aircraft when you look at it from top-down drawing. So you have the longitudinal axis, the lateral axis, and you have, say, like a nice little airplane right here, just so that we understand what we're talking about. A nice little cockpit window, so we see in which direction it's going. It has swept wings. It doesn't really matter from this perspective. Okay, so here you have a nice little airplane with the two engines. So when we talk about the thrust, all engines operating, we're basically referring to the sum of the thrust forces acting on both engines. So this TAE, or the thrust, which we saw in all cases in this diagram, so the example this one, or this one in case of the propeller, was for the case of, is basically the sum of the thrust forces acting on the aircraft. So TAE, we could say that, let's say this is T1, is the thrust force 1, and T2 is the thrust force generated on the number 2 on the right side engine. So the TAE is basically the sum of the T1 and T2. And what happens when you have an engine failure? Basically, let's say this engine dies, right? So in that case, T2 is 0. So if you have engine failure number 2 on the number 2 engine, in that case, T2 is a 0 vector. in which case TAE becomes T1, and we said that it's going to be called rather the TSE, single engine, but only in this case, right? So TAE in general case is when you have both T1 and T2, and we're going to call the TSE the single, so the thrust delivered with a single engine. So thrust delivered with single engine, right? And we can see that in general case, if both engines generated equal thrust, the thrust in the single engine is basically half. So half of the TAE, right? Because it's only, if we say T1 is equal to T2, in that case, from these two equations, we can say that TAE is equal 2 times T1 or 2 times T2, doesn't really matter. And in this case, TSE is T1, and TAE, in which case we're going to say that this equation is not true because we indexed it differently. So TSE is T1, and T all engines is, in this case, is 2 times T1. So therefore, the T single engine is basically 1/2 times T all engines, right? So it's basically fell to the half of the initial value, right? So the T single engine is going to be reduced by 50% from the initial value. If this is a like twin engine scenario and you have one engine fail. Okay, so you could fairly simply say that this is like the final drawing. However, you'd be wrong. So what happens around the center of gravity initially when you have these two forces is that the moment generated by these forces around the center of gravity, so you're going to have one moment from T1 acting on the K1 arm, is pointing in this direction. So this moment 1 would be the thrust 1 times the K1 arm, right? And you also have a moment which is the thrust 2 times the K2 arm from the center of gravity, which will be pointed on the center of gravity around the vertical axis in the counterclockwise direction is the M2, which would be the thrust 2 times the K2. Right. But what happens if we have an engine failure is that this component disappears, right? This component disappears. And along with the disappearing force component, also the moment which counteracted so the M2 which counteracted the M1 also disappears, right? So therefore we have a moment, an unequalized moment around the center of gravity, which is trying to rotate the aircraft around the center of gravity along the vertical axis of the aircraft to the right, right? So usually what you can do is you can, for example, deflect the rudder surface, and with that you generate a force pointing to the right, in this case, along, a given arm. So let's say KR, so rudder, and let's say this is rudder force. So you generate a moment so around the center of gravity, like this one, like MR, like a rudder force, which is the rudder force times the kr, right? But with this, what you did, and also something else, you would also use the ailerons to bank the aircraft to the side of the dead engine to counteract this moment, basically this unequalized moment. But what you're doing with this basically is you're increasing the surface area. You're increasing the surface area of the aircraft, and with this, you generate a very similar effect to what you would have if the aircraft was configured. And this is what we will presume. So the drag is affected, the drag curve is affected in such a way, if you have an engine failure, just as if you configured the aircraft. It moves a tiny bit up and to the left, like this. Of course, the stall speed is unchanged. So of course we would have a bit more depth, this part of the curve, like this, and it would look like this. And we could say that this is the DSE. So the drag would essentially increase. So initially we had, with regards, let's say here's the stall speed, with regards the excess thrust, we had all this big area, right? So the area between the drag all engine and the drag single engine. So between the thrust all engine and the drag all engine. So all of this area right here. Okay, and we can see that the largest excess thrust occurs in the VMD. We know that by now, right? That this would be your VX for all engine scenario for the jet. Okay, and so what happens when you have an engine failure is that your area is reduced to this one, to this smaller one right here, right? Because you're operating between the thrust single engine and the drag single engine. And therefore, it's also visible that your maximum excess thrust is going to occur at the VMD of the new drag curve, which is going to be to the left of the initial one. So this would be your VX, this would be your VX single engine for the jet. It's a reduced one. So what you can see is that the excess thrust is significantly reduced compared to the all engine scenario, and the speed for the best angle has decreased, right? So just to recollect, for the jet, in case you have an engine failure, your angle of climb is going to be reduced, like severely, and the Vx for the jet is gonna reduce. And this is what we need to remember from this whole sort of gameplay. So this leads us back to our initial conversation about the flight path angle. So we can definitely see that the flight path angle with the failed engine is not 50% of the initial one. So it didn't just drop to half, but actually we see like a much more severe reduction in most cases in the angle of climb if you have an engine failure. So assuming that you're going to have still like half of the initial capabilities that you had is just half of the story, because we also see that there's an increase in the drag as well, which further reduces with this this excess thrust which is available to you, right? And so so this leads us to the next sort of discussion, is that what happens when you have an engine failure with a propeller driven aeroplane. Okay, so when you have an engine failure with the prop, it's going to be a very similar case. So let's plot the thrust and the drag on the same coordinate axis, just like we did before, in the function of the calibrated airspeed, of course. So we're gonna have the thrust, and we're gonna have the drag, and we're gonna assume a twin engine prop aeroplane for our examination. And here we have the initial drag curve, which looks something like this. This would be the drag all engine, and you have your thrust for all engine. Now let's write a bit nicer right here. So this would be your thrust for all engines. Okay, so what happens if you have an engine failure is very convenient with the case of the thrust. Even if you have a propeller driven aircraft, the result will be the same. So the thrust force is going to drop to half of its initial value. So that's what's going to happen. So this is your thrust single engine. And what's going to happen to your drag is it's going to move. So here was the, let's say, the lowest point. Here was the VMD. So the whole curve moved basically up and to the left. So this one hugs the other one more. So up and to the left, like this. Because the same exact things, same exact effects happen as we saw for the case of the jet aircraft. So the same exact things happen. Okay, so initially speaking, we had the largest excess drag somewhere around here, right? We said it's way less than the VMD. This is your VX for the propeller driven aircraft for all engine scenario prop. Okay, right, and if this was the stall speed, like just to imagine, like in the previous scenario, like initially we're talking about this large area between the all engine thrust and the all engine drag, right? So it's this whole entire area that we have for the excess thrust, right? Is this whole area that we have for the excess thrust. But now, with the engine failure, we're between the dotted lines, so we're gonna be somewhere between these dotted lines, so somewhere right here, and this is the sort of useful area for us. This is where you have your excess thrust in case of an engine failure. Just by looking at it, you can clearly tell that there's been like a huge reduction in the useful area, a huge reduction in the excess thrust that you can generate. And interestingly, it's actually helpful to color these areas, because what you can see on this smaller area is that the thickest part actually of this area right here, this is what we're examining, is actually a teeny tiny bit to the right of the initial VX. So you can see that this would be the VX. This would be the VX for a single engine scenario for the prop, and it's very visible that the excess thrust has reduced tremendously in this scenario, but it's also visible, very interestingly, that the speed for the best angle of climb has increased a little bit, and this is quite interesting. And so the final effect is that for the case of the propeller-driven aircraft, so for the props, if you have an engine failure, you're going to have a very significant reduction in the excess thrust, which means a significant reduction in the angle of climb. And this is what we're interested in. And also the Vx for the propeller is going to increase, in contrast with the previous one for the jet, where it actually decreased. Right, so this is the main difference. So this is why we have like differences between the propeller-driven aeroplane and the jet. Right, these are the main differences. Okay, so so there's that. Okay. So a few words about the effect of wind. Now. But before we do, just a quick recap. So we talked about the angle of climb in this whole process. So this was the first sort of parameter which describes for us the climb, basically, the angle of climb, which altogether we said is basically the flight path angle, which we defined as being the angle between the local horizontal and the flight path of the aircraft. And again, the flight path of the aircraft is the path along which the center of gravity of the aircraft travels along quite conveniently. And we looked at the different influencing factors. So the first one which we looked at was the actual mass of the aircraft. And what we saw was that the mass of the aircraft actually, well, no surprise, reduced the angle of climb, right? So I think it was somewhere along the lines of this one. Yes, so it was here, yeah, the influencing factor. Even before we went into the influencing factors, we also defined the Vx. So is usually the Vx is the calibrated speed, the speed for the best angle of climb. So if the pilot maintains this Vx speed, where he can achieve the best angle of climb, this is what the airplane will basically achieve, the best angle of climb. And we'll talk about why that's useful a bit later on. And the influencing factors, as we said, the first one was the mass of the aircraft. And we saw that for the case of the jet and for basically both the propeller-driven aircraft, if you increase the mass of the aircraft, your angle of climb is going to deteriorate, right? So here you can see that we got to the conclusion that both for the jet and for the propeller, if you increase the mass of the aircraft, that's going to deteriorate the angle of climb. Okay, and we also saw that for both cases, the pilot needs to maintain a higher speed, a higher calibrated speed for a higher mass of aircraft. So if you increase the mass of the aircraft, you need to maintain a higher calibrated airspeed to get the best angle of climb of the aircraft compared to the lower mass, right? But altogether, even with a higher velocity, your angle of climb is going to be reduced because your excess thrust was reduced because of the increase of the drag. The second thing that we looked at was configuration, and of course we saw that configuration very conveniently both for the jet and both for the prop would reduce the angle of climb, and the speed which you have to maintain for the best angle of climb is reduced compared to the clean configuration for both the jet and for both the propeller. What was interesting, however, was the effect of altitude and the effect of the outside air temperature. So we looked at the effect of we looked at the case of the jet initially, and we saw that as the pressure altitude increases, so as you start climbing, for example, from the sea level up to 5,000, 10,000, 20, 30,000 feet, where these jet airplanes usually cruise, your angle of climb is continuously reducing. But if you look at the speed for the best angle of climb for the jet, so the Vx, with regards to the calibrated airspeed, it's going to be a constant. However, if you look at it in terms of the true airspeed, in reality, it's going to be increasing. And we also established that the effect for the outside air temperature is basically the same effect as for the increasing pressure altitude, right? So if you have an increasing outside air temperature, your angle of climb would be reduced, but the Vx would essentially be the same with regards to the calibrated airspeed, and it would increase with regards to the true airspeed. And when we looked at the propeller-driven aircraft, we saw a fairly similar result. So what we saw that if you increase the pressure altitude, of course the angle of climb would be reduced, but the difference is that the Vx, so the speed for the best angle of climb, would be increased both in terms of calibrated airspeed and in true airspeed for the propeller-driven one. And we also saw that for the outside air temperature is the same exact principle behind this whole thing. Okay, and we saw that the engine failure, of course, reduces, and this was the point, it reduces the angle of climb significantly, right? So we saw that even this is graphically fairly correct. This whole drawing, like the thrust dropped approximately to half of its initial value, and we had a little bit of increase in the drag, and we went from all of this big area. Well, I should use another color to highlight it, shouldn't I? Maybe this one. We went from all of this big area right here. This was the initial one, right? So we went from all of this big area basically down to this small area with regards to the excess thrust, right? So we saw a significant reduction in the angle of climb, and the Vx, so the speed where you maintain the best angle of climb, would be reduced. Okay, we also see that that for the propeller-driven aircraft, if you have an engine failure, is a bit different. So of course the angle of climb is still significantly reduced. So we went from this big area with respect to excess thrust down to this very small area with excess thrust. So of course that means a quite significant reduction in the angle of climb. However, in this case, in contrast to the jet scenario where the speed was actually less, in the propeller-driven case, the Vx is actually larger than for the all-engine scenario. Okay, and this is where we got. So we had within the different function, we had configuration, we had pressure altitude, we had outside air temperature, and we had engine failure. There's one last area which we need to discuss, is the effect of wind. So in reality, wind in performance is going to be assumed to be only a horizontal movement of air, right? So this can be explained in a few ways, and I'll start with the simpler scenario, I think, or the just a rough basically idea of what we need to understand, and then we can go a little bit into the detail. Okay, so bear with me. So here we have the ground, basically a nice old plane, and we have the aircraft climbing. Okay, so by covering this distance relative to the ground, this x, g, and d distance, the aircraft has climbed certain delta z height, right? And this is the angle, and this is the flight path of the aircraft. Okay, so where do you guys presume the flight path, or how do you guys presume the gamma, so the angle of climb, will change if you have a headwind? So headwind means that you're moving towards from left to right in this case, because your aircraft is flying like this, it's pointing in this direction, and your headwind, so the headwind would come from this direction. Okay, so how do you think a headwind changes this flight path angle? So you can pause the video a little bit and think about the answer, or you might as well just continue and find out. Okay, so the good answer is that headwind is going to increase the angle. It's going to increase this flight path angle. Let's use, I don't know, this color. I hope it's visible enough. So I'm gonna reach the same delta z vertical distance or height in a shorter x, g, and the h with headwind, because this angle is going to be increased. So the angle of climb, and this is important, relative to the ground, so this has to be reference relative to the ground, is going to be increased if you have a headwind. And it makes sense because every time your aircraft climbs a little bit, it's going to be blown back by the wind to this flight path, if you think about it. Or always a little bit, and relative to the air, you're going to have the same flight path as this pink one, as this one right here, right? But altogether, you're always going to be blown off by the wind backwards a little bit, and at this point, so actually the drawing is not correct with this regard. So how you could imagine it, I'm just going to draw it in a little bit more detail. So this scenario right here, because I want you guys to understand clearly what's going on. So here we have the two flight paths. So this is the ground, and here you have the initial flight path, and delta v, or delta z, sorry, delta z, and here you have the one with the headwind. Right, it's a very heavy headwind, and the wind is blowing from this direction. It's a constant wind. Okay, so initially, the aircraft is at the same position in both flight paths. But as the aircraft continues and is reaching, let's say, the first position, so this one is the pink one, is the still air condition. It means that this is the flight path of the aircraft relative to the air, and this is going to be the same flight path relative to the ground if there is no wind. However, because there's a wind, actually the aircraft at this time frame is going to be a bit rearward of this aircraft, right? Of the initial one, of the no wind condition, because this one is going to be the headwind condition. right? It's gonna be blown back a little bit by the wind. So it's a bit higher than this initial one at this given, number one step. In the number two step, little bit higher, this initial aircraft is still on the pink flight path, but this wind right here is blowing the aircraft back on the flight path. So therefore the one with the wind is going to be even further back of the initial one. And maybe at the third second the aircraft is even further ahead, and you still have the wind blowing from here, and your aircraft being blown by the wind is going to be even further away. So it's the same height but further away because it was blown back by the wind. It was blown back by the wind, so it's the same height, it's at the same altitude, but more rearward than the other one. And let's draw a couple more so that you guys understand or see the process better. So here you have, the 4th second, and the wind is still blowing, so the aircraft is even further to the back. And here you have, the last second when the aircraft is at the top right here. Its nose is kind of ugly, but don't worry about it. You have the wind blowing from here, and our little silhouette airplane is right up here. So the aircraft is now finally at the top. So you can see that we went from this flight path right here, and I'm trying to find a color which is like very different from the two. I think they should do it. So we went from this center of gravity, and we slowly started to be blown away from the wind, nice and continuously, and we were finally blown into this position, right? And this is how it looks like, right? So at any given state, you could draw up these triangles and get sort of the same result. But the end is that you had these little single steps where the effect of the wind is sort of added up in every single second, and this is what makes sense. So between the two centers of gravity. So we started from the same position, and we always get drifted a bit back, a bit rearward. And this is sort of the point. Okay, so if you have a headwind, in this case, you're going to be your flight path angle is going to be increased, and you're going to reach the same vertical distance or the same height at a sooner position. And when you have a tailwind, it's the exact opposite effect, because in that case your flight path angle is going to be reduced, and you reach the same delta z at a later point. So your flight path angle is going to be reduced, and your GND, so the distance you cover on the ground, is going to be increased in case of a tailwind. So usually how I index wind components is H, dW is for the headwind. So in this case, HDW, and TLW for the tailwind. That's just a simplification. Okay, so we could go ahead and play the same process, with the tailwind, but we're not going to do that for now. I think you can all see that this is all sort of the same process you could do for every single step that you take here. If you have, a tailwind, you're gonna have at every single second a secondary root, which is gonna be the same exact effect, just the opposite way, right? So actually you could have like a secondary aeroplane right here, which is always being drifted off, and you know it's going to be a very complicated drawing, but you know, let's go with it. So these little airplanes are going to get further and further from each other, you know, as time goes by. So these airplanes get further and further away from each other until at the very end, you know, this would be the effect of the tailwind. So it blows you off in this direction in this case, and we could easily see that in this scenario what you have is basically a flight path which you have a flight path which basically looks like this compared to the initial one, right? So the more like mathematical solution, so we can establish that if you have a headwind, your angle of climb is going to be increased, or your flight path angle is going to be increased. This is the same basically expression. And if you have a tailwind, your angle of climb is going to be reduced and your gamma is going to be reduced. Okay, so the more mathematical approach that you could have to this is that your flight path angle is basically a distance which you cover on the ground. So, you know, there you have the ground, and here you have a distance. So is a distance, so x, g, and d is a distance covered on the ground, and then you have a delta z, and then you have this flight path angle, right? This gamma angle. And you guys remember that we have something called the gradient and percentage, maybe, that is the tangent of this angle, which is the delta z over the x, g, and d. Okay. So we can calculate these distances basically with so these are distances. If I want to calculate distances with simple, very simple kinematic expressions, I can say that the distance is the velocity times the time, right? So this distance, the vertical distance which I climb, is going to be equal to the rate of climb, which is the vertical climb, times the time it takes for me to get to this delta z. And this rate of climb, what's interesting about it is we're going to see that it is unaffected by the wind, because we define the wind as a horizontal movement of air. So there is no change in the vertical movement, so the rate of climb is always going to be a constant. So this delta z in a given amount of time, so this one is constant, so this delta z is in a given amount of time is going to be a constant. And we can go and calculate this x, g, and d as since is basically a distance relative to the ground is going to be the ground speed times the time. And this is where it's going to become interesting. So two kinds of speeds which we mentioned. So we have the ground speed, which is relative to the air, relative to the ground. And we have the true air speed, which is the speed relative to the air. Right? And how we can sort of calculate one from another is we're going to see that the ground speed is the true airspeed minus the headwind, or the true airspeed plus the tailwind. I think it makes sense, right? If you have an airplane which is traveling relative to the air, so you have a true airspeed of 5 knots, or sorry, I don't know, let's say 100 knots. And if you have a tailwind, so you're traveling relative to the air, so the airstream around the wings is, traveling or lending you a true airspeed basically around the aircraft, or actually it's the undisturbed airflow speed which we talk about, is 100 knots. And but the mass of the air relative to the ground, this whole mass of air in which you're traveling, is moving, so this whole mass of air is moving in this direction, and actually just one quick correction right here. Right now we're gonna presume like the VTAS to be acting from the aircraft side, right? So we're not discussing aerodynamics, where it doesn't matter whether the air flows around the wing or the wing flows around, or the wing moves around the air. But we're gonna say that the aircraft is moving relative to the air with a true airspeed, with the magnitude of the true airspeed, and the whole mass of air in which the airplane is flying is moving with 5 knots, let's say in this case. And this would be a tailwind because it's blowing in the same direction as the aircraft is moving. That's how a tailwind is defined, by the way. So it's blowing in the same direction as the aircraft is flying towards, right? So in this case, the 100 knots, and this would be 100 knots in this example, the true airspeed. So if there was there was me on the ground, observing this whole thing, what would I see? What would I see? How fast the aircraft travels? Of course, I don't see like the air molecules and how fast they're moving and how fast the aircraft is moving relative to the air. No, what I see is just the absolute movement of the aircraft relative to the ground, because that's what my eye can see. And it's going to be the sum of the movements of the aircraft relative to the air mass and the sum of the air mass's movement relative to the ground. So the sum of the two effects, so therefore I'm going to see that the aircraft is moving relative to the ground with 105 knots. So with 105 knots, and this is called the ground speed in this case, right? So from my observation, the aircraft is moving relative to the ground with 105 knots, when in reality the aircraft is just moving relative to the air with 100 knots, and the mass of air in which the aircraft is flying is moving with 5 knots relative to the ground. But this is what I see, and this is what is the ground speed, and this is what counts for a lot of things. And if it was the other way around, if I'm observing from the ground, and I have an airplane. Which travels, let's say it's a small aircraft, Let's say it's a small, really small, I don't know. I'm just trying to make something up, I don't know. It can actually happen to some towing motor gliders that, let's say they're going to be flying at 50-60 knots. So this is like a very small, towing motor glider. Maybe looks like a Cessna. I don't know. And I'm going to be extreme here just so that you guys see this example. So I have this Cessna in the air, and maybe it's going around like almost at its, like stall speed, but it's moving relative to the air, and it's moving with let's say 50 knots. 50 knots. And this is, yet again, this example is going to be extreme. And so there's this area of mass around it in which the Cessna is flying is going to be moving backwards. So I'm going to have a so-called headwind. So the wind is blowing from a direction in which the aircraft is flying in, right? So it's blowing from the direction in which the aircraft is headed to, and the headwind component is going to be 50 knots. And this is interesting. Okay, so the aircraft is flying relative to the air mass with 50 knots, and the air mass is moving relative to the ground with 50 knots backward. So here I am again, because I have nothing better to do. I'm standing around and watching all these aircraft, doing weird stuff in the air. So I'm observing the Cessna, and what do I see? How do I see the aircraft's movement relative to the ground? And if your guess is that I'm going to see the aircraft hover, so basically not moving relative to the ground, staying at the same altitude, your guess was right? Because the ground speed, as I've already written up here, if you have a headwind, is going to be the true airspeed minus the headwind. So the 50 knots minus, of course, 50 knots is, of course, 0 knots. So the aircraft is moving relative to the air with 50 knots, and the air mass is moving relative to the ground with 50 knots backward. So I see the sum of the effects, not each individual step. But in reality, you would feel like the aircraft is like, oh my God, it's probably like the air is stalling, above the wings, because it's not moving forward. It's not generating any relative movement. But here's where relative motion of air comes into play, and this is why it's very important, because in fact there is relative movement of air around the wings. So lift is being generated, right? So you're going to have the lift and you're going to have the drag because there's relative motion of air, but this whole air mass is moving relative to the ground as well. And this is where it can be very, very interesting. And getting back to the other example, there's been some very unscientific posts about I think it was something along the line of 737 or A320 or just a normal commercial aircraft, flying at Mach 2 or something like that, so twice with the speed of sound, because they calculated from the ground speed that it was twice the speed of sound. It's possible that the ground speed, if you have a very, very strong tailwind, if you're flying in a jet stream, for example, which is a very, very strong wind, it can happen that your ground speed, so your speed relative to the ground, is going to be very, very large. But what matters in the Mach number calculation is the true airspeed over the local speed of sound, right? So interestingly, your ground speed, if somebody was observing from the ground or at their home computer from live ATC or not live ATC, Flight Radar 24 or something, they see the ground speed and they would calculate that, oh my God, this aircraft is flying above the local speed of sound, but actually in reality the true airspeed is what counts. And so both of these lessons is important, or both of these scenarios is important, because what's important from aerodynamics point of view and how the aircraft is flying is what happens between the relative airflow and the aircraft. But from this perspective, and sometimes from performance, is very important also what's happening relative to the ground, and this is when we need to take into account the effect of the wind. Okay, so we can see from this whole gameplay how this formula for the ground speed is true and correct, right? And what this whole thing means is that the distance, this xg and d, so the ground speed times the time, is going to be very much affected by the wind, right? Because if you have a headwind, is basically going to mean that the ground speed is going to be the true airspeed minus the headwind. So therefore, this ground speed, if you have a headwind, is going to reduce, right? But the t, the time it takes you to get from this given altitude or given height to the delta z, to climb this delta z height, is going to be a constant. So therefore, the xg and d is going to reduce if you have a headwind. So this whole xg and d is going to be reduced if you have a headwind, xg and d headwind. But the delta z remains the same at this point. And this is the interesting thing where we try to get, is that in this case it's very visible that the angle of climb is going to be increased. So now what happens if you have a tailwind? If you have a tailwind, your ground speed is going to be equal the true airspeed plus the tailwind. So this ground speed is going to increase with the amount of the tailwind. The time is going to be a constant. So therefore, this xg and d, if you have a tailwind, is going to be longer. So it's going to be xg and d tailwind, like this whole thing. This whole distance is going to be the xg and d tailwind. The delta z is essentially going to be the same. So what you can see is that the flight path is going to be shallower and the flight path angle smaller. And we finally get to the same end result as what we were trying to get to understand here. So altogether, what we're saying is that is this very simple notion that if you have a headwind, your angle of climb is going to increase, and if you have a tailwind, your angle of climb is going to decrease. Okay, so I would end this video right here. I would like to thank you for your attention, and I'll see you in the next video.